afternoon, student. Welcome to the lecture of Real Analysis 2. In the last lecture, we have seen an introduction of Lebesgue measure. We have seen that this Lebesgue measure was first introduced by a French mathematician, Henri Lebesgue. His life tenure is 28 June 1875 to 26 July 1941. And first time he was given a notion that whatever the length of interval is there, this cannot be used for an arbitrary set of real numbers. Therefore, there is a need to have a generalization of length of an interval to some measure of a given set. Therefore, this measure concept was introduced by Lebesgue. That's why it was called as Lebesgue measure. And this measure is the generalization of a word length in one-dimensional space, area in two-dimensional spaces, and volume in three-dimensional spaces. So whatever this measure we were going to define, it will be a function defined on set and having non-negative real numbers, including plus infinity, right? But in general, whatever this measure we were going to find out in an n-dimensional space is called as an n-dimensional volume, n-volume, or volume. And this concept was this was given in the year of 1901. Therefore, whatever is the length of an interval is generalized to measure of set of real number. We know the property of finding the length of a finite interval. How we were finding length of any interval is b minus a, where a and b are the endpoints. Now this interval may be of any type: open interval, closed interval, semi-open, semi-closed. With this, what are the properties carried out by this length of an interval? First, length should be non-negative. Second, length is defined for any interval. Length of union of intervals is summation of length of the corresponding intervals. Length is translation invariant, right? Now, what is translation invariant, that we have discussed already. We want to construct a set function, say small m, which assigns to each set of real number a non-negative extended value, okay, defined on the curly m set. Curly m is the collection of sets and it is denoted by m of it. Therefore, m basically we were defining as a function on curly m, that is collection of sets, to the domain is R plus union infinity, right? Therefore, what should be the properties of those m function, measure function, defined for an arbitrary set E? First thing is, measure should be defined for any subset of it. Any subset of R means this curly m, whatever is under the consideration, must be a power set of R. Then for an interval, this measure should coincide with length of an interval. Third, M is translation invariant. Fourth, for any disjoint sequence En of subsets of R, measure of union is summation measure of the corresponding set. And this property is called as countable additivity, right? But what we have discussed, unfortunately, such a set function satisfying all the conditions 1 to 4 do not exist. Therefore, we have to restrict the function instead of power set of R to sigma algebra. Okay, how this is, that will be coming into our further study. Therefore, the first point we were going to introduce is we were going to define a first measure called as an outer measure. So today we were going to understand what is outer measure. Okay. As of we have discussed, measure should be a concept which is generalization of length. And the important fact known to us is length can be found only for intervals, not for the arbitrary subsets of the real number. Therefore, if someone is interested in finding the measure of a set AC, someone is interested in finding the measure of set AC, then first job we will do is we will find out all possible coverings of this set A in terms of intervals, right? Therefore, here one can find out the covering union IN. Now, these covering should involve intervals specifically. Why we were containing the covering involving intervals only? Because we know for intervals we can find out the length. For intervals we can find out the length. How many such coverings are going to exist for an arbitrary set? Suppose I am taking an example. Set A I am going to define to be a set 1, 2, 3 finite set. How many such open coverings are going to exist? What do you think, students? This is number 1, number 2 and number 3. How many open coverings I can find out? See, I just want open intervals. Therefore, here let us mark the intervals like this, covering all the points. Therefore, the first interval let me call I1, second let me call I2 and this third let me call I3. Therefore, whatever the set we have written 1, 2, 3 is contained in union IN I equals to 1, 2, 3. Right now, one can take the more intervals as well, like this. Correct, no? And all those will work as the coverings, rather open coverings I call, because all those are the open intervals and this will become the open curve. Therefore, the job we will do, we will find out countable collection ion of open intervals such that A is contained in union ion, and then for every covering we will find out the length. For every covering we will find out the length, and infimum among all the length will be defined to be an outer major. Will be defined to be an outer major. Let me write the definition. For each set A of real numbers, each set A of real numbers, consider the countable collection. Consider the countable collection ion. Countable collection ion. Simply we can write ion, or one can write ion in front 1 to infinity, 1 and a safety, of open intervals, of open intervals that cover A. That cover A. How many such coverings are going to exist then? Infinite, one can say, na? Is contained in union n equals to 1 to infinity IN. Right now? Infinite coverings are there, yes or no?
Yes, ma'am.
Suppose I take only one point in the set. Okay, so the set under the consideration is only 1 point, say 0. How many open coverings one can find out? First open interval covering this 0, right? This will be one covering. If you just add two more open intervals, whether it will be open covering or not, that will be my second covering. Let me add more intervals, that will be also an open covering. But adding each one open interval give you one open covering. Therefore, how many such coverings are going to exist? Infinite, no?
Infinite.
Yes. Among the infinite coverings, first we will find out the length of every covering, and whichever gives us the infimum value will be the major, rather an outer major of the given set. Let me write, we define an outer major. We define outer major of A by, how I am going to define? This is M star is the notation we were using. M star of A is infimum of. Infimum of what? Length of the covering. How can you find out the length of this covering union ion? Is it summation length of ion? Right now?
Yes, ma'am.
Length of ion such that A is contained in union ion and running from 1 to infinity, where L of ion is length of the interval. Ion. Is that okay? Understood how outer major is defined? In order to find out the outer major of any set of real numbers, we will first find out the covering of open intervals. Right now, we will find out the covering of open intervals. Why intervals were taken only? Because for intervals a major is defined and it is nothing but the length of the given interval. Therefore, for open intervals we can find out very easily the major, that is the length. That's why the covering of open intervals is found, and then among all such infinite coverings we will find out the length of all the coverings, and whichever covering is giving us the infimum length will be the outer major of the given set. Okay, any doubt in the definition of outer major?
No, ma'am.
No, ma'am.
I think there is no doubt in we have infinite open coverings as well, right? As I shown here, for a singleton 0, one open interval is one covering. If we just go on adding one interval, one open interval in the open covering, it will give you a separate open covering. Therefore, adding one open interval will give us one open covering. How many such intervals we can add? Infinite intervals we can add. That's why we have infinite coverings of the given set A in terms of open intervals. As of for A, set A equals to 1, 2, 3, I have shown you. Right now? Yes or no? For set A, let me elaborate again. Which interval I have taken? I1, let us say I1 is taken as 0.5 to 1.5. Right? What I1 I am taking? 0.5 to 1.5, right? Let me take I2. What I2 I want to take? I can take I2 as 1.5 to say 2.5, right? Next I3 I will take. What I3 I will take? 2.5 to 3 I will take. Therefore, if I take the union, whether the three numbers will be included, 1, 2 and 3. 1 will be included here, 2 will be included here and 3 will be included in the third interval. Therefore, if I take union I equals to 1 to 3, 1 to 3, all the three numbers of the given set A will be included. Therefore, this becomes a one covering. How many such coverings we can write? Is it essential to write the intervals in this way only? No, one can write
No,
intervals in
ma'am.
this manner. No? Around 1, you can find out any interval. Around 2, find out any open interval. Around 3, find out any open intervals. Right? Therefore, there are infinite coverings for a given set. Among all the infinite coverings, first you find the length of every covering, then get its infimum value in order to have the uniqueness. Can we find suprema instead of infima here? Suprema of length of the intervals. That will be difficult, no? Because as we have infinite number of sets, many bigger coverings are also available, right? But it is difficult to find out the suprema of length of those open coverings. Therefore, we are sticking up to infimum of length of such a open covering, and whichever is the infima value will be the outer major of the set A. I hope the definition is clear. If once the definition understood, then only you can understood the rest part of this outer major. Okay. Now let me go to understand some properties of the outer major M star. Properties. Okay, what are the properties possessed by this M star? First, I can say that this is a function defined on power set of R. Right now, for any set we can do this procedure. For any set of subset of real numbers, we can do this procedure. The first property one can write is M star is a set function from power set of R. I will write power set of R to non-negative extended real numbers. Non-negative extended real number. That is, M star is defined as power set of R to R plus union infinity. R plus union infinity. What is the second property I will write? What about the nature, as we were saying, non-negative? Therefore, may I say M star of A is always non-negative for any set A. For any A in power set of R. Is it okay? Two
Yes,
properties.
ma'am.
First is defined for any set. Therefore, domain is power set. Codomain is non-negative extended real number. And every outer major is non-negative. Right? Why it is non-negative? One can check. Actually, M star we were finding infimum among the length. And what about length? Length is always a non-negative quantity. Therefore, every element in this set is a non-negative real number. So what about the infima value? This infima should be non-negative again. Correct, no? Every
Yes,
element in
ma'am.
this set is non-negative, right? Now we will go for the third property. Now the third property tells us that outer measure of an empty set is 0. Outer measure of empty set is 0. Now one may have a question how to find out the outer measure of an empty set. For empty set, our job is to find out only the open interval covering empty set. Okay, so one can write any interval, any open interval which will cover empty set. No? Therefore, may I write like this? Phi is contained in the open interval minus 1 by n to plus 1 by n for all n in capital N. Therefore, this open interval works as a covering of phi. Yes or no? Empty set is contained in this set. Right? Then what about the definition of outer measure? By definition of m star. What about m star of phi? This is infimum length of this say minus 1 by n to plus 1 by n such that phi is contained in minus 1 by n to plus 1 by n. Is that okay? Okay, what about the length of this interval? Can anyone tell me the length? Minus 1 by n to plus 1 by n. Yes. This is minus 1 by n. This is plus 1 by n containing 0. Right? For every n it will be a covering, no doubt. Na? For n equal to 1, for n equal to 2, for n equal to 3 and so on. For every value of n, this will be act as a covering. Therefore, what about the length of this interval? Yes, students. Length of the interval minus 1 by n to plus 1 by n.
2 by n.
Yes, it is 2
By
by
n.
n. Upper bound minus lower bound. You have told us in the last lecture. Na? Therefore, this is 2 by n. 2 by n for all n we were writing. Na? 2 by n for all n in n. Right now? And what is the inferior value? Inferior of this set 2 by n for n in n. Is it 0 or no?
0.
0.
Yes, it is 0. Inferior is 0. Therefore, n star of phi is 0. That is outer measure of an empty set is 0. Any difficulty in this property?
No, ma'am.
No, ma'am.
Let me go to next again. Number 4 we were going to prove for a singleton set. If capital A is singleton set, can anyone guess what will be its outer measure?
The element itself.
No. It is very similar to this aspect, no? Phi, if I assume as an element, we have said that this is
0.
open curve. Yes, it is 0. How? Let us check. Okay. Let me write A to be a singleton set, say X, for any X in R. Right. Now the job is to find out the open covering. How can you find out the covering of this element, single element? This is somewhere X, no? And I want to find covering for this. Can I write the covering again as of we have done in the third part? This is x minus 1 by n to x plus 1 by n. And again for every n this will be the covering of the element x. Right? For every n it will be a covering of an element x. Right? Therefore let us use the definition again. Therefore m star of A is infimum of. Okay, first here I should write A is contained in x minus 1 by n to x plus 1 by n for n to be a natural number. Therefore, this is infimum of length, no? X minus 1 by n to x plus 1 by n. Okay. Again, shall I write n in n? Now, what is the length of this interval again?
2 by
2 by
n.
n.
Yes, it
2
is
by
2
n.
by n. 2 by m for n in n. Same situation we have obtained. What is the inferior value?
0.
0.
Zero.
0.
This outer measure of singleton element is 0. Is there any difficulty in finding the length? Shall I show you
No,
here?
ma'am.
Length,
No,
how can
ma'am.
you find? X plus 1 by n minus x minus 1 by n. Right now, upper bound minus lower bound. Okay, therefore x will get cancelled. 1 by n minus of minus 1 by n. This 1 by n plus 1 by n is actually giving us 2. Okay. Therefore, if A is a singleton set, we have proved that the outer measure is 0. Let me go for a next property. This is monotonic. M star is monotonic. What is the meaning of monotonic? Here it is, if A set A is contained in B, this will imply M star of A is less than or equals to M star of B. This is what monotonicity property is. Okay, let us prove this. The only hint we have is A is contained in B. Okay, now if A is contained in B and suppose we found the covering of set B. Suppose we find covering of set B. Will it work as a covering of A as well? Right now? Because if it is a
Yes, ma'am.
covering, this
Yes,
B
ma'am.
will be included in say IN or IK 100. This is say union IK. If B is contained in union IK, A is contained in B will imply A will contained in union IK. Therefore, this IK will work as a covering for both these sets. Right now, IK will work as the covering of both the sets. Therefore, here we will take only IK to be the covering. Okay, let union IK be the covering of B, which will be also a covering of A. Which will be also a covering of the set A. Okay. Now let me define two different sets, say E1 and E2. What E1 I am going to define? I am going to define this E1 to be a set of all sum of length of the intervals. Okay, k equals to 1 to infinity, assuming A is contained in union IK, k equals to 1 to infinity. Is that okay? And later if I find the infimum of this set, it will be outer measure of this A. Correct now? Here I can write infimum of E1. What it will be? It will be outer measure of the set A. Right now? Let me write second set E2 to be again sum of length of the intervals k equals to 1 to infinity, no doubt. Here we were considering B set. Therefore, B is contained in union IK, k equals to 1 to infinity. Therefore, again if I take the infimum of this set E2, it will work as outer measure of the set B. Outer measure of the set B. And what is the aim to prove actually? M star of A is less than or equals to M star of B. Right? Therefore, our aim is to prove this set E2 is contained in E1. Claim is to check E2 is contained in E1. If E2 is contained in E1, what about their infimum relation? In general, if I have a subset A, set A is contained in B, if I take infimum on both the sets, what is the relation? In the
Less
infima,
equal.
E2 greater.
infima A and infima B. What should I write here? Either it is less equal or greater equal. If A,
Infima is less.
so here you tell me what should I write? Infima is less. I don't understand actually. What should I write? I think you are seeing my screen. A is contained in B. I want a relation between infima A and infima B. What should I write? Should I write less equal
Yes, ma'am.
or greater equal?
Less equal, ma'am.
Is everyone agree with this? All students. Yes, whether all students are agree with this? Let me make it more clear by taking an example. Suppose I am taking a set A of numbers say 1 to 10. Okay? Numbers say 1 to 10. Right? Now I'll take initially a subset B of A, say 5 to 10. And once I want to take a set B to be 1 to 5. Now you have to tell me the respective infimas. What about infima of A?
1.
1,
What about infima B?
5,
5.
What about infima B here? Or let me write
1.
B1,
1,
B2. Why to make confusion? Let me write B1 and here it is B2. Here it is 1. Now check. If I take a subset B1 of A, this gives us the relation between their infimas as infima A is equal to, sorry, B1 I am writing now. This is strictly less by infima of B1, right? Hello,
Yes, ma'am.
ma'am.
right? Now if I am writing B2, what if I am writing for B2? This is infima of A is equal to infima of B2. Okay, reverse I have taken B1 as a subset of A. Here I am taking A subset of B, na? A change of notation I have made actually. Right now? Now in this case, if B1 is a subset of A, that is, let me combine both the possibilities. If B is a subset of A, what it is giving us? Once it is giving us strictly less, when it is equal to, therefore combining both the cases, can I write infima of A is less equal by infima of B? What kind of inclusion? B contained in A. Here I have written A contained in B. Therefore, what should be a relation here? This,
Greater equal.
yeah, it is greater equal. Getting me? A notation I missed actually. If B is subset of A, infima of A is less equal by infima of B. Similarly, if A is subset of B, infima of A is greater equal by infima of B. Is it clear? This is not less equal. Here is actually a big mistake students were doing, right? Let me close the example now. Therefore, in order to prove, if I prove E2 is less than or equals to E1, what it will prove actually then about infima relation? Infima of E1, infimum of E2. What should be a relation?
Greater than equal to.
And this is less than or equals to, no. E2 is a subset of E1. E2 I am saying subset of E1. Therefore, infima of E1 is less equal by infima of E2. I think you are still confused with infima values. Okay, whichever is the subset will give us the greater infima, that you have to remember. Therefore, here E2 is a subset. Therefore, this E2 should give us the greater infima. Okay, and that is what the claim now. M star of A is less than or equals to M star of B. Infima of A less E1 less than or equals to infima of E2. I hope it is clear now. Okay, Now what is the job? What is the claim we were making? E2 contained in E1. Whenever I want to prove E2 contained in E1, how should we prove this? We start with one element in E2 and we will prove that the same element is in E1, right? Okay. Now let me start with an element E2. If I start with an element of E2, this will be sum of length such that B is contained in this union IK. Now I want to prove the same thing. A is contained in union IK. Okay. So let X is in E2. Is that okay? I have taken element X in E2. The aim is to prove X is in E1. If X is in E2, therefore X is summation of length IK such that B is contained in union IK. So let me write X equals to summation K equals to 1 to infinity length of IK such that, what such that? B is contained in union IK, K equals to 1 to infinity. Now if we just check the restriction on the set even, what it is? The value is same, summation length of IK, but the condition is A is contained in union IK. Now here anyhow we will try to make it as A is contained in union IK. But what is the relation given to us between A and B?
A is contained in B.
Yes. Therefore shall I write here such that A is contained in B, contained in union IK. Therefore what it is will give me actually?
A is contained in union IK.
Yes. Such that A is contained in union IK. If A is contained in union IK, therefore may I say the element X is in E1 now? Right now? Element is in E1 now. Therefore we have started with an arbitrary element X in E2. We have proved that it is in E1. Therefore it gives us the idea E2 is contained in E1. E2 is contained in E1. And let us just use the infima relation. Because what this infima relation gives us? Infima of E1 is less than or equals to infima of E2. But what is infima of E1? This is M star A. And infima of E2 is M star B. Okay. Hence the proof we have made for A contained in B. A contained in B implies M star A is less than or equals to M star B. If you just go through the Roydon's book, they have written directly this E2 is contained in E1. They have not given the proof of E2 contained in E1. It was assumed that students were knowing this, and then they have written directly M star of A is less than or equals to M star of B. Any difficulty after this?
No, ma'am.
To other students also?
No, ma'am.
No, ma'am.
Good. Now actually the next proposition, now we will check whether this outer measure is going to satisfy all the properties of that length what we have defined. And if it do so, then only one can say that this outer measure is a nice generalization of the concept length. But in the further propositions, we were going to show that outer measure of the interval is length. That is, it is going to assure us that this is the generalization of a concept length. But what are the remaining properties of the length? That also we have to check. No? What are the properties? I have written. Yes, here it is. Okay. What is the property? Length of an interval. If what we were expecting from measure of an interval is length of an interval, and with this outer measure, this property is going to hold. That is for an interval, we were going to prove that outer measure is the length. Similarly, outer measure already we have defined for the subsets of R. Also, we were going to prove M star, that is outer measure is translation invariant, but this number 4 property, that is countable additivity property, is not going to hold in case of measure defined to be an outer measure. Then one may have a question, not going to hold means what it is going to hold, or how can we check this? Then in case of outer major, we were going to prove that this major of union is less than or equal to. That is, instead of this equal to sign, we will have it as less than or equals to. I should not write here actually. Okay. Therefore, this property of countable additivity will not be satisfied by the outer major, but instead of this equality, we will have less than or equal. That is inequality we were going to get. We were going to get inequality. And with this inequality, the name of the property becomes, instead of countable additivity, we will call it as countable subadditivity. We will call it as countable subadditivity. And then we were going to check the remaining properties with some examples as well. Okay. Any difficulty in today's lecture? If you have, you can ask me. Today we have seen outer major and all its properties also. For the prepositions, we will move ahead in the next lecture. Yes, any difficulty in today's lecture? If you have, you can ask me. If not, let us stop it here for today's lecture. Thank you for being with me for this today's lecture.